So welcome here to the defense of Dmytro Bogatov. I'm very happy for Dmytro and for this day because Dmytro came here in 2017. Before that, he graduated from high school in Kiev in 2013. And then he went to WPI, where he graduated with distinction in 2017. And then he joined directly VU in September. And then, he started PhD with me, and I have been very fortunate to have Dmytro as my student, let me say this, from the beginning. And, and I'm very happy that with this day today. During the PhD, of course, he did the master. He got the master in 2019, again with distinction. And, he did an excellent work, and I hope that you will see today in his presentation. Also let me mention that Dmytro, the family is connected now from Ukraine, that I would like to say that we support and stand with the people of Ukraine, and we hope that this will finish soon and will continue the life free and dignity. Okay, so
thank you.
Dmytro, you can.
Thank you. Well, thank you everyone for coming to my doctoral defense presentation. I hope you will like it. The topic of the presentation are different query types executed securely in the outsourced database setting. And before I start my presentation, let me say it's dedicated to my country, to Ukraine, to the brave defenders of Ukraine fighting against Russian invasion, in particular to our dads, Konstantin and Igor. Thank you. And let's get started. In the introduction, I will talk about the concept of outsourced databases, which queries we aim to support, and which adversaries we are going to fight off. The motivation for this work is that companies nowadays accumulate, store, and process vast amounts of information. They increasingly turn to cloud solution for managing and storing this data. And the obvious challenge is these solutions has to be both secure and efficient. Let me introduce a concept of outsourced database system. Imagine a thin client, small client, but trusted clients, for example, premises of a company, and large, powerful, but adversarial, untrusted server. This is a setting where we need to execute a query. Usually, some indexing structures go on client, some keys go on client, but the data goes on the server. In the setting, we can still execute queries securely and efficiently. And let me say what we mean by securely. When server is untrusted, we say that there is an adversary which can observe and do something on this untrusted server. And we differentiate two types of adversaries. The weaker one is the snapshot adversary, which can steal your memory snapshot. That's why it's called snapshot. It can steal your hard drive, RAM snapshot, but it cannot interfere with your server execution, and it cannot persistently monitor. That's the snapshot adversary, a weaker one. And the stronger one is a persistent one, which on top of snapshot can also monitor what your server is doing. It can monitor the network, the number of packets, the traffic, the size of them, the timing, and your accesses to the secondary storage. That's called access pattern, when you made access to which memory location in which order. That's a persistent adversary, a more powerful one. And the query types we want to support, at least in the context of this thesis and presentation, are point queries, when your attribute is compared to a categorical value. A range query where your attribute needs to be between endpoints, and a k-nearest neighbors queries where you have a concept of object and distance, and you need to return k-nearest objects to your query from the space defined by your objects and distance. Let me mention the works I have published during my PhD program, and roughly the presentation flow will be a chronological order of my works. The first one is VLDB work 2019 about range queries in the snapshot adversary model. The second one is absolute point and range queries in the persistent adversary model, the stronger adversary. Recently completed work, QAnon running similarity search application in outsourced database system, where the core of the similarity search is essentially a KNN query. And the last one is not a part of this presentation, yet I'm very proud of it. It's about pure cryptography, anonymous credentials, where a person can prove a fact about oneself without revealing anything extra, without revealing identity or any values. This section is the smallest one, and I will stop after each section for the questions. This is the comparative evaluation of audio revealing encryption schemes and secure range query protocols. This is exactly range queries in the snapshot adversary setting. This work is essentially a systematization of knowledge, comparative evaluation. The problem is one of the conventional ways to run range queries in the snapshot adversary is taking a conventional index like a binary tree, B+3 index, and then encrypting its values with a special type of encryption which preserves the order. If A was less than B, then the encryption of A will be less than the encryption of B. Then when you encrypt the entire index with that, you can simply use it in any conventional range query algorithm. So what we've done is we've noticed that there are a lot of schemes offered in the literature. Each of them claims to be the most secure, the most efficient, and state-of-the-art, but you cannot directly compare one to the other. You don't know which one is really best. And to make matters worse, when you try to replicate the results, you discover that some of the schemes have not been implemented at all, or have poor prototype implementation, have different security definition or benchmark methodology. We've solved with it with systematization. We have developed an evaluation framework, a unified framework with a unified security definition and benchmark methodology, and we analyzed in depth the 5 OP or schemes we have chosen and 5 extra secure range query protocols. In particular, a novelty of our benchmark methodology is that we did not simply run the schemes and protocols against the wall clock time to simply see how many milliseconds or seconds it takes, because it would depend on hardware, software, and primitive implementations. Instead, we counted something that the scheme essentially cannot fake, the usage of a certain cryptographic primitive for schemes, or making an I/O request, input-output request, either to secondary storage or to the network for the protocols. With that, we have analyzed 10 solutions in depth. That's the output of our work, and even a few surprising results. For example, that the primitives, the protocols which were believed to be slow and inefficient, like putting the entire index in ORM, turned out to be not the worst. So we've given it a chance in my next work. Any questions on this one? I'm glad I explained it well. So the next work is absolute. Now we aim to execute point and range queries in the persistent adversary model. The snapshot adversary model is good, but adversary can only see the backup of your data, the snapshot of memory, your hard drive. What about the adversary which, for example, is a malicious script which can monitor the entire execution of your program on a server? In particular, this script can sniff your network and see how many packets, which size you transfer and when, in response to which queries. And the script can see your accesses to the secondary storage. For example, it can correlate a query with the particular set of records you touch during the query execution. It's been shown in the attacks that this leakage alone, communication volume or access pattern, is enough in certain cases to do a complete reconstruction attack. If I know some auxiliary data, then I can essentially guess the content of the database with high enough probability. So the conclusion is we need to protect against this kind of leakage as well in the outsourced database setting. A conventional way to protect against the access pattern leakage is called ORAM, Oblivious Random Access Machine. It's a protocol between a client and a server. That's why it can be naturally put in the outsourced database system. And in this protocol, essentially a client makes more requests than necessary. It's kind of a fake request in a certain fashion to obscure the real requests. And there are theorems and constructions which say that the best you can do in terms of efficiency is you have to do an extra log n request for each real one you make, where n is your data size. It seems expensive, but I will show you that you can optimize. What do we do about communication volume? Essentially, the best we can do is again return more records than necessary, essentially adding fake results and then let client filter them out locally. But the question is how much noise and in which way to add so that we have a mathematical guarantee on security and privacy, and we add the minimum amount of noise so we stay efficient. I can tell you right away that adding a constant noise or uniformly sampled noise will not work because adversary can filter that out. The solution to that is differential privacy. Now we'll go over a few background blocks so that you can understand the solution we propose. Differential privacy is a property of an algorithm which takes a database, a collection of records, and returns something of that database. It can be a query, it can be count query, range query, but most important, it's not a method by itself, it's not an algorithm, it's a property of an algorithm. And in particular, suppose that there are two neighboring databases. Neighboring means that they differ in exactly one records. For example, say it's a medical database and the patient Jake is in the left but not in the right database, otherwise they are equal. So we have two neighboring databases and we have an algorithm which runs essentially a query on a database. So differential privacy says that probability of understanding which of these two databases was used as an input to algorithm A by looking at its output is bounded by these two parameters. How do we make sense of these parameters? E to the epsilon, for small epsilon, is essentially a 1 plus epsilon. You can approximate that. So epsilon is the difference in probabilities which you allow. If they differ in 0.1, then your epsilon is 0.1. Delta is an additive term, so it has to be small by itself because it's added to a probability. And you can think of it as a probability of the entire system failure. Because if a differentially private mechanism is inside a system and the system fails, obviously you lose privacy, so you incorporate that information in delta. Now you can wonder, how do you then construct a differentially private algorithm if differential privacy itself is only a guarantee? Fortunately, there is a way, a generic way. It's called Laplace perturbation method. It's been proposed in the original paper which introduced differential privacy, calibrating noise to sensitivity. So what you do is you sample noise from a certain Laplacian distribution, and if you do that, then your resulting algorithm will be differentially private. How you do that is you sample noise from Laplacian scaled proportionally to sensitivity of a query and inversely proportional to the epsilon. Sensitivity of the query being how much the output changes with respect to input. Say for a count query, if you add one record or remove one record, your count changes by 1, so the sensitivity is 1. So you sample with a scale 1 over epsilon. But then you may say, okay, Laplacian distribution is symmetric. It spans from minus infinity to plus infinity. What happens if you sample a negative value? Can you add a negative noise? No, you cannot. And you cannot simply discard it, because then you would have been sampling from another distribution which is not Laplacian. So what you do is you shift the Laplacian distribution to the right in a positive direction by exactly the amount that you have a guarantee that you will never, or say with a low probability, get a negative result. And we do that in absolute. We derive this value, this new mean of a distribution, so that we know that we will not sample a negative value. And the last thing about, yes?
So just to clarify, the reason we can't sample a negative value because ultimately what you're dealing with is communication volume, and that cannot be negative.
Yes, and
if just releasing numbers, they could be negative.
Yes, yes. That's correct. So there are differentially private mechanisms which do not add noise, and they can deal with negative values. But what we do is essentially, yes, this value will be a noise which we have to add. We cannot subtract it. So then we have to shift the Laplacian distribution. It still has to be Laplacian. That's the problem. It cannot be truncated. But the only way we can do is we can shift it left and right. The last thing about differential privacy I wanted to mention, the way I describe only works for a single query. Because if you keep resampling Laplacian values, adversary may be able to filter them away. So what you do instead is you sample the Laplacian noise once during initialization for your entire data set in a certain fashion, and then you use those noisy values to answer all queries. This is called differentially private sanitizer, and the process called sanitization of data. So you deliberately add noise inside the data itself. Here I show an example of a sanitizer we're going to use for range queries. It's called hierarchical sanitizer. Imagine you have your data in a range from 0 to 80. It can be, say, an age of a person. And then you split it into 8 buckets of 10, range of 10 years. And you sample a Laplacian value into every bin. And then you add those fake records to the records in the bin. Then when you need to answer a range query, you return the entire buckets where the range spans. And what makes this sanitizer hierarchical is that if any subset of your buckets are from a single parent, you can use that parent instead and save a little bit on the noise.
So what are the numbers here?
The numbers are, the red number is a hypothetical noise, the green number is the real number of records. So you can see that when you go up and you use parent, the noise is smaller. So that's why if your range is big, and instead of getting, say, 4 buckets, you can take 1 parent, then you can save in noise. All right. Now the next question is, now that we know that we need to protect against both communication volume leakage and access pattern leakage, can we come up with a definition of security, not yet even a construction, just a definition of security, such that satisfying this definition will mean protecting against those leakages? Turns out, yes, we can, and that's one of the main contributions of our work. Computationally differentially private outsourced database system. So let me parse it for you. Imagine that you have again neighboring databases which differ in one record, Jake, which is on the left and not in the right. Now imagine that you have m fixed queries which you execute in the outsourced database setting. Suppose that the adversary can monitor the server during the execution of these m queries. Now, the probability that the adversary will know which of these 2 databases was used, whether Jake was or was not in the data set, is bounded by this very differential privacy guarantee which I just described. That's the beauty of this definition. And the advantages are manifold. First of all, the entire view of the server is protected. Not only communication volume, not only access pattern, not only network or memory, the entire view, whatever adversary can see, is a fair game. This definition, of course, implies protection against access pattern communication volume leakages, because if the adversary sees any of that, she can break the definition. The query sequence is fixed. This inherent for this definition. Essentially, the argument is an efficient system cannot return the same number of queries for the short range and the long range. I have an example for that. And if you allow an adversary to adaptively choose the queries, adversary will be able to guess the output of the former queries by looking at the number of records returned for the latter queries. I want to know that this limitation is inherent for this setting, not just for our definition. And finally, the negligible lambda term there is to say that the definition is computational and not information theoretic. Information theoretic definitions of security allows adversary to have unbounded resources computationally and time-wise, but we need bounded resources. We depend that adversary has bounded computational resources. All right. And here, yes. I can tell if you want. The question is why we need computational resources.
No, the query sequence is fixed.
Oh yeah, I have a nice appendix slide. Why do we have to have fixed query sequence? Why do we not allow adaptive query sequence? I will show you by example. Suppose that the two neighboring databases we're talking about are medical databases, and the one different record has a rare medical diagnosis, Alzheimer's disease, which correlates with the senior population. Now suppose that the adversary knows how a medical professional who is a user is doing their queries. And the medical professional first queries for this very rare and serious diagnosis. If there is a record with such diagnosis, then the professional queries only the senior population, because there is a correlation. But otherwise, she queries the general population. Now you can see that the number of records we return in both these cases will be vastly different. In one case, it's only seniors. In another case, it's the entire population. Adversary can obviously see that. So the adversary can guess reliably the answer to the first query by looking at the number of records returned for the second query. To protect against that, we will essentially need to return the same number of records every time, which is not feasible. It's not going to be an efficient system. That's why we do not allow adaptive queries. Good? All right. Now, here is the construction. A single-threaded absolute. We have a client on the right and an untrusted server on the left. And the algorithm is like this. The user makes a query, for example, from 40K to 50K. The client then goes to a local index, which is small, and understands that there are 6 records, for example, which satisfy this query. Then the client goes and grabs the noisy counts from the sanitizers we're talking about, which blots the number of records, say it's going to be 9. And then the client makes requests, these 9 requests, to the ORAM, which obscures access pattern. Then the client obviously filters out the noise from the returned records and returns them to the application. As simple as that. ORAM hides access pattern, and the usage of sanitizers hides communication volume.
How does the client know what to request from the ORAM?
Client maintains a small index of records, mapping a record ID, the attribute value to a record ID.
Okay, so that's for the 6 honest records, and the 3 fake ones
are going from the sanitizers.
They're fixed, or it doesn't matter what they are?
They are, yes, they are created at the setup.
Are you asking for the records?
You need to ask for 3 fake records, in addition to the 6 real ones.
Yes.
But it doesn't matter which 3 you ask for?
No.
It's ORAM.
It's fake, yes.
Okay.
All right. You may reasonably ask, is it fast? I will tell you, no, the single-threaded absolute is not entirely fast, so we need to make better. We need to do better. We need to parallelize. The natural way to parallelize is to split data set into M partitions, and then we can maintain a single client, but M different ORMs running on different machines, which we can execute requests in parallel. It's all nice, it's all easy. However, what do we do with our sanitizer? Can we maintain one sanitizer for M partitions, or do we need to maintain sanitizer per partition? We have explored two ways. Starting with a separate sanitizer per partition, what happens is the amount of noise this sanitizer generates is essentially the same or close to what you had in single version absolute. So when you save by splitting the number of real records over M partitions, you lose because each of these M partitions has the same amount of noise with a single threaded version. So you amplify your noise M times. That's one way to do it. And the other way to do it is maintain a shared sanitizer for all ORMs. There is a mathematics in my paper on how to generate the noise in this case. But I can tell you that it's going to be more than single-threaded, but not by much. Let's say it's alpha of the original fake record size in the single-threaded. So now we have it M times F or alpha times F. So obviously the way we are going to use is depending on whether alpha is less than M, which it is. We have checked it practically and theoretically that pretty much for any reasonable number of M parallelization factor, the alpha is going to be less than M, and the shared sanitizer implementation is going to be more efficient. I will show you the plots at the end.
So the cost here is essentially the number of records?
Yes. Yeah, that's actually a good question. We can obviously benchmark how much it takes to make a request and transfer it over the network, but everything in the system is essentially proportional to the number of records you return. And here is the diagram over parallel absolute. It works the same way as single-threaded, except the last step is parallelized. You start with the query. The client grabs the actual number of records from the local index, then goes to a sanitizer, grabs the fake number of records, the noise, and then the client distributes all these requests among ORMs. They execute in parallel. A few plots. First of all, yes, shared sanitizer method is much better. First, it overperforms the separate one in pretty much every parallelization factor we've tried. And you can see that shared essentially drops linearly, the overhead drops linearly with the added parallelization, which is essentially a whole task of doing parallelization. We want scalability close to linear. And final plot, how does absolute fare against other solutions? On the left of absolute are conventional, not secure, optimized for performance databases, MySQL and Postgres. And on the right are solutions which provide comparable security guarantees. Linear scan is when you encrypt the entire database, download it every time, every query, decrypt it, and then run the query locally. And shrink wrap is another solution from the literature with the comparable security guarantees.
20 minutes?
Yes. They use garbled circuits, NRM.
But it's for the linear plots?
To be honest, shrink wrap does more than just range queries. So they advertise it as a solution which can run complex queries, where range is just one component. But we have benchmarked it separately.
So what was the setting again?
1 million 4 kilobytes uniformly sampled records with the domain 10,000.
And the servers and the client?
64 threads, 8 VMs.
And how far they were?
Different geographical regions. I believe it was east and west coast of the US. I believe 20 milliseconds ping. Good?
Can you go to slide 10 for a second? I have a question. Yeah, so here, so the client is getting the IDs from the local entity of the
Yes.
non-fake
Of the real records, yes.
records, and then the fake records from the sanitizer on that side, right?
Yes. I want to show that the sanitizers are public.
Okay.
So it can be on the untrusted server, it can be just in the cloud, it's a public knowledge.
So this might be a nice question, but is there any risk from the fact that essentially you're taking the fake data from a different source? Maybe someone can learn something from that?
No, that's the beauty of the differential privacy guarantee. You can outsource this information and you will be fine. Okay. Any more questions about the absolute in general? Recent work published in CCS 2021.
By the way, so go back. In the sanitizer, you get the total amount of records.
Yes.
Not
Yeah, just. I see.
That's why it's public.
You remember when I had a slide with these buckets and. Yes, I see. This one contains the plus, the total real plus fake.
Real data and the big data.
Yeah. Okay. Exactly what you see after you execute the query. Okay. So that's why I said.
Alrighty. Then the last work I want to talk about, recently finished, QAnon, secure similarity search in outsourced databases, a clever reference to K nearest neighbor and privacy. Thanks, Dasha. All right, so this time we go back to snapshot adversary, the one which can steal memory at any point in time, and now we want to try K nearest neighbor queries. The nearest neighbor search requires a definition of an object and a distance. An object can be a location, 2D, 3D, or it can be a vector for a document, an embedding, a set of features, keywords, anything. A distance can be a usual Euclidean distance, how far one object is from the other on a plane, or it can be an inner product distance. And then the query, the application, can range from give me 5 nearest restaurants to give me 3 most similar documents. We will explicitly target similarity search, so our object is an embedding, and our query is give me similar documents, and our distance is inner product. Our approach is similar to how we do it with OPEs and OREs, order preserve and encryption, to apply a type of approximate property preserved encryption to the inputs so that we can apply existing nearest neighbor search algorithms naturally. And the goal of the study is to see how accuracy of search correlates with an actual practical security. First component is we need approximate property preserving encryption. First of all, which property do we want to preserve? One may say a distance, but we can be smarter and say that when you do a nearest neighbor search, you don't care about actual distance, you only care about what is closer and what is farther. You care that A is closer to B than C is. Therefore, the property you really want to preserve is called distance comparison. Why do we need approximate? At least we want to shield against frequency finding attacks when the same points will be mapped to the same ciphertext, and adversary will be able to see how many of the same points you had initially. We have a recently published work by our friend Adam, distance comparison preserving encryption scheme, which gives a guarantee like this. If a distance between x and z is larger than the distance between x and y by more than beta, then the encryption of z will be farther than the encryption of y from the encryption of x. Parse this for a moment. If they were sufficiently far away from each other, we will preserve a distance comparison. If they are too close, we do approximation and we may not preserve it. And the way it works is for every point like x, y, and z, we first sample a point in the beta radius of a hyperbole around this point, and remember that the dimensions can be many. It's not just 2D, 3D, it can be 700D. So we have a hyperbole, we sample a point in a hyperbole beta radius, and then we extend it to some amount, and that's our encryption. And on this plot, you can see that if the circles, the original circles beta radius did not intersect, then the larger ones will not intersect. But if they did, it may happen that you will lose the distance comparison, which is by design. Now, equipped with the distance comparison preserving encryption scheme, we can design a set of experiments for the search accuracy. Essentially, our outsourced database system protocol is simple. For each value of beta, we generate a key, we encrypt data set and query set, we run queries against data set, encrypted versus encrypted, with the conventional nearest neighbor search, and then we report some accuracy metrics. And now in detail, the data set we use is from information retrieval field, TREC 2020, which has almost 9 million documents embedded with the ML, natural language processing transformer BERT, which results in 768-dimensional embedding for each document. Then the query is another embedding with the same BERT of a query sentence, and the query is asking for the k, 1,000 most similar documents depending on inner product distance. Yes?
Each dimension is an integer or?
A float, a real number.
Okay.
Why we use TREC for that and not...
So what is BERT
Yes.
again?
BERT is the bidirectional representation transformer. It's a natural language processing algorithm, which essentially, it's a trained ML model, so it's a large file. It takes a document, it produces an embedding.
Reaches 768 floats for each.
Yes. It's a very high dimensional space, hard to imagine hyperbole. Why we use TREC is because when you do embedding of a document to the vector, you lose already some information. So you cannot just run a pure KNN and then see how close your result is to the expected one. You lose something already. And TREC dataset allows you to know the actual result in terms of a human perception, in terms of how humans rank the documents. So you know what the 1,000 most similar documents are in reality. And then the metrics we report, a few for pure KNN, a few for the similarity search. For pure KNN, we report the distance from one result to the other, how many operations, edits you need to make to get one from the other, and a distance, essentially how many documents are missing from the necessary 1,000 documents which has to be in the set. And then we also report ranking quality, recall, mean reciprocal rank, and normalized discounted cumulative gain. Don't remember what exactly they do, but they take into account relevance and not only the position of the document in the rank. And here are the results for this kind of experiment. We have run it for the beta from 0 to 50, and here is the plot. We have put distance and difference metrics as percents of the k of 1,000. So when you see 0.5, it means 500 documents. And what you can observe here is, first of all, distance degrades very fast. Even for small beta, even the small perturbation results in many edits. So you have to do a lot of edits to get one set to the other. The difference grows almost linearly, essentially every new, yes?
When you say one set and the other, one set is what got revealed without encryption, what you could retrieve with KNN without encryption.
Yes.
And the other is what you can retrieve with KNN with encryption.
Yes.
So comparing this 1,000 to that 1,000.
Yes, yes. So here we don't care about the content of the document and embedding, we only care that the approximation in the encryption scheme itself did some perturbation. And I want to measure that specifically. The difference grows more linearly. Essentially, every new degree of perturbation knocks out a few correct results from the set. And the ranking quality metrics, they expectedly drop and drop simultaneously, which is good, which essentially proves our assumptions. X, this, the beta, that's beta. Yes, that's the radius of that ball from the picture, the necessary distance between 2 points so that the distance comparison between them will be preserved. If they are too close in terms of this beta, the distance may not be preserved. All right. Now the next task is we need to assess security. We can obviously take a look at the scheme itself and see that it provides some frequency attack protection, some bitwise protection, but we need some practical notion. So we need an attack which works against our solution, plain text, and then we add our encryption and see how the attack works against the encrypted data set for different values of beta. The attack we have chosen is black box inversion attack from the embedding attacks, a recent CCS 2020 paper. What they do is they recover a set of words from the embedding. You remember originally the embedding mechanism BERT converts a sentence to the embedding, and then this attack recovers those words from the embedding. The difference is BERT needs an ordered sentence with all the stop words, but the attack recovers a set of words unordered. But it still can be devastating. Suppose if it's a patient file, it can potentially recover a name, a diagnosis just from the embedding. How they do it? They train an LSTM model, 30 epochs, to recognize the correlation between document and the embedding. They train and validate on a book corpus dataset, but we will do it on our own TREC. First of all, we have obtained code from the authors, thanks to them for cooperation, and we have run the attack against the book corpus dataset. We have confirmed their results, so we know that the code works. The way we run an attack, we have a few approaches. First of all, there are two baselines, the two efficiencies between which the encrypted is supposed to lie. The first one is a plain text, no encryption, essentially the original attack from the paper, but run on a TREC dataset. And the second one is random. When we don't even encrypt embeddings, we simply produce random embeddings. That's an equivalent of symmetrically encrypting them. And supposedly, the efficiency of the encrypted attack should be within these two. No better than the plain text, no worse than the random. Then we think, how can adversary in reality, in practice, attack our outsourced database system? If an adversary has access to the embedding model, to the BERT, to the fine-tuned, customized BERT we have, then the adversary can train on this data set. It can produce its own training data set and train on that. But if adversary does not have access to that, adversary will have to only observe the encrypted embeddings produced by our system. And therefore, we have two models. In public model, we train on plain text but validate on ciphertext. In the private one, we train on ciphertext and validate on ciphertext. And lastly, how do we measure the attack efficiency? The authors of the original paper offer usual in the ML field precision, recall, and F1 score. But on top of that, we add the number of stop words. Why do we do that? BERT needs stop words, those common English words like articles, pronouns, and so on. BERT needs these words because for the context, and it needs context to produce an embedding, for the context, these words matter. But the attack model, it only gives back the set of words. So what we have observed is that in a lot of cases, the attack only produces these common words. And we don't want to give it credit for just that, give it high precision or recall. So we want on top of the F-score, we want to measure the percentage of stop words. And here is the experimental result. A lot of lines. The punctured lines on the top are the plain text baseline. The precision, recall, F1 score, and the percentage of non-stop words, the real, say, sophisticated words. On the top, the plain text. On the bottom, the punctured lines are the random. Supposedly, we should not get below that. And the solid lines are the encrypted from beta 0 to beta 15. A few observations. First of all, the efficiency of the attack expectedly degrades with the encryption with the approximation term beta. Second, the attack already drops efficiency once we even introduce beta 0. So even exact preservation is enough to make it less efficient. And you see that after a certain beta, the values of the efficiency drop even below random. How can it happen that encrypted is doing worse than random? We have checked, and in random case, the model only produces stop words. So the model learns from the random embeddings that each sentence has a comma, period, the, and that's all. And then the model confidently predicts those words and does it right some % of the time. When we do encryption with a higher beta, the model attempts to predict sophisticated words and fails to do so, and is being penalized for that.
So where is the random again?
This for recall, this for F-score, this for precision, and somewhere, and here for the support. So you see that for random, it's almost 0. So for random, all the words it predicts are stop words.
What's F1 score, or is that just
Harmonic mean of precision and recall.
Oh, so it's inferred. You can infer it from the
Yes.
other lines.
Yes. It's just that if you need a single number to describe precision and recall, use F-score. All right. And now that was for the public when we can train on the plain text. And this time we train on the ciphertext and validate on the ciphertext. And you see that essentially the results for encryption are the same as for random. The model simply is incapable of predicting anything beyond stop words. So we conclude that at least for the case of private model, when the adversary does not have access to the embedding model mechanism, the protection our approach gives is pretty much absolute in terms of at least this attack. All right?
How realistic is this?
Realistic is what? So that the adversary does not have access. I would say pretty realistic, because even if you use BERT, we highly fine-tune it. So what Hamed did, it's not a plain text BERT, it's not a, how you call it, a bare bones BERT. They have retrained it. But it would be a nice experiment to compare plain text BERT with the Hameds and see. Yes?
So let's say you have a hospital that encrypted its records and is looking for similar case histories.
Yes.
Right, so our documents are case histories. The records are encrypted, and the adversary has no access, so private model feels right, because there's no public model.
Yes.
But then the adversary has access to some other hospital's database that got leaked because it got leaked. And so you have a similar data set, but not the same.
If that other data set and hospital use the same embedding model.
No, they just use plain. Yeah, I just got the plain. I just got no records. No.
Here,
no embedding.
here, public versus private means, does the adversary have access to a mechanism which takes a document and produces embedding?
Oh, I see.
No,
Okay.
but what Leo asks is that if another hospital uses a different BERT but similar,
That would probably depend. We didn't have this experiments, but it would probably depend how similar that BERT is.
I'm just trying to understand, is that public or private or somewhere in between? And we don't know the answer.
I don't know.
Okay.
All right. And the last slide here, we now put everything together on the same scale the attack efficiency and the search accuracy. And what we give to practitioner is first a clear trade-off between search accuracy and attack efficiency, the security. And we can see that, for example, the DCP encryption scheme that we use, they have a proof that for square root of the largest vector, you already have half of the bits hidden, and that's only the very first purple line. Then we also plotted the actual vector lengths and double vector lengths. So we can conclude that even for a very reasonable security here, the search accuracy is still high. It didn't drop much, but the attack efficiency did. Not only it dropped from the beta 0, it also dropped from the plain text. So we conclude that our approach is viable, efficient, and secure. Now that you have no questions, I think I proved it. All right. And the final slide, the conclusions. First of all, practical, reproducible, and again, practical. A lot of works are either purely theoretical, or they don't have implementation, or they have poor implementation. The work which is not reproducible is not a work. So the whole purpose of offering another system, mechanism, or a scheme is so that it can be used in practice. For that, there has to be at least an implementation. Other researchers like myself need to be able to reproduce. That was the whole purpose of my first work. The second is property-preserving encryption, although cryptographers seem not like it, is practical. It does not provide ideal security by definition, and sometimes leak even more, but it's practical, as we prove it in KNN work and my VLDB work. Just be honest in quantifying the leakage and benchmarking the scheme itself. Other conclusion is, as I have seen in absolute, even the primitive which is supposed to be heavy, like differentially private sanitizers and RAM, the system at the end can be fast if you are smart about optimizing it, parallelizing it, and running it on a specialized hardware. So don't be afraid to experiment on primitives which are considered heavy. And finally, for the outsourced database system as a whole, we only need to add a couple of query types, like joins. Lina would add that soon. And then we will be able to build the entire outsourced database system and run it in the cloud.
For the question will be how it will compose, right?
Oh yes, yeah, that's a different direction.
Compose with
yeah, the different, if you have join the in terms of security.
Over time, we didn't. All right, now any questions about the entire presentation? At least the public part of it. Yes.
So one question is, a number of times you talked about the snapshot versus persistent
Yes.
security model, and you talked about property preserving encryption, like order revealing encryption.
Yes.
Right? Is that, I mean, is that known to be secure, the snapshot model?
What do you mean known to be secure?
Well, we have a security model, I guess. Snapshot.
Okay, let me paraphrase it. If you ask how realistic is this model in real life,
I'm not asking that. I'm not asking that.
or you mean is OPE or even secure in a snapshot adversary? Well, when you define security of OPE, you give a leakage profile. Very ironic, yes. When you say secure in a model, you always give a leakage profile. We did it in absolute, we did it in all the OPs in a review analyzed. So you give a leakage profile, and then it's up to practitioner to decide if it's worth it or not.
I mean, absolute was different because it's differentially private, right? So that's,
Yes.
That's just like that's a privacy.
I mean, we still leak, say, timing. we still leak the fact that the query was made.
In absolute.
Yes.
Right. Okay. No, I just wanted to. I mean, I wanted to understand like what is the. Yeah, I guess you answered my question.
Okay. Good.
And I have a couple.
Any questions about DCP? It's your scheme, after all.
Yeah, I had one actually. So this attack that you mentioned, it's like learning it's like
Yes.
it's like an ML attack.
Yes.
Is it obvious that you can't do something to the attack to compensate for the fact that the data is being encrypted and then have the attack work again? Like, I mean, is it kind of robust to this?
That's a good question. Let me say that this attack, at least this one, seems to take one embedding at a time and trying to extract knowledge from it. So, but what our encryption does, it encrypts a single embedding well, but then if you look at the whole picture, because we do preserve distance comparison and to a certain extent distance itself, then say a cluster of points in plain text will correlate with a cluster of points in the ciphertext. But the attack does not seem to take that into account. Maybe there is a better attack which would take the whole picture, the whole data set, and learn something from it.
Yeah.
So we have to look at that.
Yeah.
Yeah. Or maybe design a new attack.
And then one other question. So for absolute, can you say something about the like semantics of the privacy guarantee versus the use cases? So we have a differentially private type of security privacy here, right? And so I think because I think one danger for like applied researchers is to treat this like semantic security or something, right? That basically you're not leaking any information about it. But can you say something about like whether the guarantee that we give actually makes sense in like use cases of interest?
Yeah, I see. So in human language, the guarantee of absolute would be a differentially private guarantee. If the adversary is such as we described, the persistent one, which can observe everything, that adversary will not be able to say if a particular record was or was not in the database. No.
I mean, that's the thing, is differential privacy is not...
Well, with certain probability, of course. Depending on the parameters of epsilon and delta and lambda, I can set it in a way that the probability of adversary learning the difference will be very small. So that's the guarantee. Obviously, to achieve that, we also do encryption, asymmetric encryption, so the adversary does not see the value of the record itself. But the guarantee is the record being or not being in the database.
I guess what I was getting at is that differential privacy, like if you would say that it doesn't tell you whether a record is in or out of the database, right? That you would think that's it, but that's not different, right? So differential privacy says that there's some epsilon, which is like 3 or something, right?
0.3, yes, it's small. It's a difference in probabilities.
That you're 3 times as likely to see some value, like so. Which is, I mean, maybe it's a criticism of differential privacy as a whole, but
yeah,
particularly in this context, like, because I guess what I'm saying is like differential privacy, the typical, the originally imagined usages were like studies, right? People would participate in a study, and you would either give your data to the study or not.
That's how it originated, yes.
Yeah.
There
so
were
you talk
attempts
about
to...
databases, right? And you say that a record is either in the database or not in the database.
It is a novel approach to apply to a database setting, indeed.
Yes.
I guess in the experiments, what is the epsilon set to? You showed some graphs
Uh,
of efficiency and so on, but what is the security?
I believe it was ln2, which is 0.7, something like
Okay.
that.
Okay.
But we changed that. So you changed that.
Yes, yes.
Yeah, we did that.
In the original paper, there is plus, like when you vary epsilon.
Right, so the guarantee is, right, let's say I want to know if my record is or you want to know if my record is, right? The guarantee is that by running this query, your certainty about my presence in the database changes by a factor of 1 plus epsilon, like I said you want.
And is that good or?
Right. I think it depends on the social processes that follow.
Yes.
Like, what does that mean? Does that mean you put me in prison? Does it mean you ostracize me? Does it mean you don't take me to your grad school? That's very
I guess here's another way to ask my question is that in differential privacy you have a utility trade-off, right? You want to do a study and you want the outcome of the study to be useful, right? What is the utility trade-off here in absolute? I mean, what are we getting out of the fact that we're making the
The overhead, essentially, because what we add, we filter out on the client. So the downturn, the disadvantage of adding noise, in our case, it's only overhead. It does not affect
So you're
the
saying
accuracy of the query.
You're saying that for the price of
Yes.
the price of efficiency,
Exactly.
I'm going to make it so that you only are 3 times
Exactly.
rather than like 0 times.
Yeah.
Yeah, it's interesting.
If audience doesn't have questions, I guess there is a closed part as well, where a committee keeps asking me more questions.
No, let's,
I mean, I had a quick follow-up.
Yeah.
Not exactly the same question, but so you talk about, you discuss about the order preserving schemes.
Yes.
And, essentially, I just want to know more a little bit about that. Like, if we have a preserving scheme, every query gives quite some information because now we know things about the structure of the data. So I just want to understand, it's a little bit on the same flavor about the practicality of order preserving schemes. If and how much more they leak and when they are really practical. Any comments on that?
It's a good question. Well, first, pretty much every audio preserving or revealing encryption scheme, almost everyone, reveals something beyond just the order. There is a leakage profile. It can be as bad as half of the bits, or it can be as small as equality pattern. On top of that, you by design reveal the order, and there are attacks which exploit that. But they still depend on some auxiliary knowledge, some number of queries, not queries, but only auxiliary knowledge, but there are attacks. And that's why we moved to a persistent adversary setting.
Right. So the rules are that anybody who is faculty gets to stay and grill the candidate more. Thank you all. And then eventually
I will stop the Zoom and the recording.